Let's continue our discussion on relativity and bring in more concepts, more experiments. What we're looking at picture here is what's called the light cone. And if you ever go into physics or astronomy, concepts like these cones of light, of what you can and cannot see, are going to be objects that you'll study very often. So let's talk about an idea called a cosmic shower. And here's the principle, right? A cosmic ray comes in and hits Earth's atmosphere. So you hit Earth's atmosphere. Earth's atmosphere is just a collection of a bunch of atoms, high up there, floating around, flying around rapidly. And then all of a sudden, this high energy particle will smash into that atmosphere. And what does that do? Well, it creates this cascade effect. This guy will hit our atmosphere and kaboom, make a big explosion. And that explosion will send more explosions out. And so when we say our cosmic showers, what we're talking about is this guy here breaking apart in our atmosphere, smashing our particles together, and making just this giant shower of subatomic particles that came out of this initial impact. Why do I talk about all this? Well, I need to talk about one specific one. One particle that comes out of this is called a muon. We're not going to delve into its properties, other than to say that a muon at rest will have an average lifespan of about 2.2 microseconds, 10 to the minus 6 seconds. All right, very, very short lifespan. So, reminder. This particle, this high-energy cosmic ray particle, will smash our atmosphere and create this pancake, is a term they actually use to describe this. This wave of particles smashing down onto Earth's surface. And the muon is one of these particles in that wave. But, once again, we've got a seeming conundrum to discuss here. That muon, left to its own devices, will just decay, fall apart in 2 microseconds. However, this distance here, light from here to here, that's about 50 microseconds. It'll take light about 50 microseconds to go from the surface up here. And that muon decays in 2 microseconds. So, a question for you. If light takes 50 microseconds to travel that far, and a muon decays in 2 microseconds, can we ever detect a muon with ground-based telescopes? Can I ever set up a telescope on my desk here and just wait for the cosmic ray to come down, smattering the atmosphere, and wait for that muon to fall down and hit my detector? So, I will say, yes, the muon is a charged particle, but Earth's magnetic field is not going to be able to accelerate these things. You can't go faster than light. So that makes no sense. There's still the possibility that they decay in time. But we also have these relativistic concepts of time dilation and length contraction. So it turns out that, yes, I can do this experiment. I can set up a muon detector and wait for the cosmic ray particles to produce them and let them smash through my detector, my ground-based telescope. And it works off of time dilation. Those muons are going to be moving at relativistic speeds. And so the time delay it takes, from the muon's perspective, yes, it'll live for 2 microseconds. From our perspective, that fast-moving object, its clock will go slower. And the slower its clock goes, the more likely we are to see that muon. So let's keep talking about this. Let's talk about our classical versus modern physics, okay? Try and get more at these weird differences. Classically, right? If I stuck you in a rocket ship, I gave you as much energy that you could imagine in the universe, and I just let you fly off through the cosmos, and you're going on a constant rate. This rocket can boost itself effectively forever. Well, here's a plot of how much energy you've consumed and how fast you're moving. Effectively a plot of your kinetic energy. The more energy that I push into you, the faster and faster you go. And there's no limit. Right? I just keep pumping more energy into you, and you can keep going faster and faster. And this is classical physics. I have X amount of energy, I'm going to go Y speed. It's that straightforward. But when we start taking into relativistic effects, there's a problem. Look at this plot here. This is a plot of your speed ratio to the speed of light. And wouldn't you know it, 1 is the speed of light. In this graph here. You can't go fast than the speed of light. Laws of physics literally dictate that. If you are a particle, if you have mass, you cannot exceed that speed of light. So classical physics breaks down. It does not work. We need to look at relativistic physics. Now, this is a strange world we live in now. That asymptote's back, right? We cannot surpass the speed of light. Cannot. The more and more energy we pump into our rocket ship, eventually it starts to tamper off. We can keep pumping more and more energy. That's what this plot says, right? The further we go in this direction, the more and more energy that we are pumping into that to get that rocket going faster and faster. And it does not matter. We could pump an infinite amount of energy into this, and we still haven't quite reached an object moving at the speed of light. So the kinetic energy, a relativistic correct expression for the kinetic energy, goes as this weird gamma factor times your mass in the square of your speed. So let's talk about what this gamma factor is. This is going to be our Lorentz factor. In essence, it's a measure of relativistic effects, right? So here's a plot of it. We're going to look at your speed relative to the speed of light. So you can be not moving at all, or you could be moving approaching the speed of light. What happens is that this Lorentz factor blows up. Right? So the equation for this, right? Gamma, dimensionless quantity. Number, square root of number. Speed divided by speed, just a number. So this thing unit-wise is just a numberless quantity. Look what happens, right? If your speed is 0, 1 minus 0 is 1. 1 divided by square root of 1 is 1 still. So if you're at rest, this gamma thing is 1. Now go faster and faster. As our speed increases, as we start going faster and faster, as their speed approaches the speed of light, this ratio becomes closer and closer to 1. 1 minus 0.9 is 0.1. So now I have 1 divided by the square root of 0.1, and that blows up. As your velocity approaches the speed of light, this Lorentz factor starts to diverge. It blows up. And so this Lorentz factor, that's a mathematical way to quantify this idea that you can never reach the speed of light. It's in this definition. You cannot reach the speed of light. The universe would blow up if you could. With the caveat that you're mass. If you're a photon, you obviously travel the speed of light. Let's bring back that cosmic muon. Let's bring that guy back in. Remember what we said, these cosmic muons, they're created in Earth's atmosphere, upper atmosphere. And they'll have a lifetime of about 2 microseconds. And I said, Earth's surface is just too far away. Light takes tens of microseconds to travel that far. And so to explain this, we have to formally define what we mean by time dilation. We have this delta t prime, gamma, the Lorentz factor, delta t. So what's happening here? Right? Delta t without the prime. This is the time that the muon experiences. How much time transpires for that muon. And so in that muon's frame, we'd call it its rest frame. In that muon's frames, it lives for about 2 microseconds and then decays. It fades away. But come to our Earth-based observations. Put a little human here. got any? Let's do that color. So, ooh. Wow, that was awful. So here's our little stick figure human trying to detect those muons, trying to see those coming in. Right? That's the time that we measure delta t prime. We see a fast-moving particle, it's fast-moving muon, and so it lives for a longer time span. That's what the delta t prime means, right? As the speed goes up, as the velocity goes up, gamma gets longer and larger and larger, which means the time of life in our reference frame gets longer and longer. And so what happens in this idea is that a bunch of muons get created in the upper atmosphere, and the faster they go, the larger the number of muons that we'll detect, because they're moving fast enough that they can live long enough in our reference frame in order to hit the surface. Related to this time dilation, think back to that relativistic snake, the length contraction stuff. So the length contraction, similar formula. Length contraction goes as the proper length divided by the Lorentz factor. And so the way we'd say this is that L prime is the length that the muon measures, whereas L is the length we measure. Muon's in this moving frame relative to ours. So we'd say, look, here is L, right? Just this length. We measure 35, 15 kilometers in this picture. We measure this height, whereas the muon, well, it's going to measure a much shorter distance. From the muon's perspective, the distance from Earth's surface to Earth's atmosphere will be significantly smaller. Could be as small as meters if the muon's going fast enough. So the distance from the Earth's surface to our upper atmosphere is shrunk down for the muon. Yes, physics is incredibly weird, but this is accurate. This is very weird. Basically, for the fast-moving objects, things become squished. That's one way to think of it. That's what I mean by this length contraction. All right. Let's do another thought experiment. All right. More thought experiments. Let's put you in that rocket ship. Let's have you going super fast, right? So I'm going to have you in a rocket ship that's going 99.9999% the speed of light, just super fast, right? And now I'm going to put a mirror in front of you and ask, what do you see in that mirror? What's happening in the mirror? Well, is the mirror far enough away from you that photons are bouncing off you haven't quite reached the mirror yet, and so you can't see an image? Or has enough time transpired? You're having this kind of like time delay effect? Is it just you length contracted? What's happening here? So I'll tell you that you're going to see yourself perfectly normal. Remember, you're in an inertial reference frame. In your frame, right? It doesn't matter how fast the rocket ship's going. You're on the rocket ship. As long as that thing's not accelerating, things look perfectly normal to you. You see yourself in that mirror as a normal image here. However, if you had a friend on Earth with a telescope and they're trying to track you, look at yourself in your own mirror, weird, they'd see a very strange phenomena. Here's a little animation I'm pulling up to simulate what's happening. We're going to compare your measured contraction versus what your friends would see of you. This is what your Earth-based friends would see of you. On the left, we have this measured contraction. As the object's going faster and faster, remember that length contraction, the faster an object is, the more squished it becomes. So that'd be the length that we measure. Now on the right, I have this visual appearance. What does that mean? Well, here's what's happening. As the object is going faster and faster, light, remember, in order to see this object, a photon has to hit this and bounce back. Hit this and bounce back. Well, this object, photon hits here, but then it moves. So now a photon hits here and reflects. And it moves. Hits here and back. So yes, we would measure you, right? I'm looking at you looking at yourself in the mirror. You would be this length contracted object. But the image I see in the sky would be this strange kind of blurred, swept out image of you. Swept out because of how fast you're moving before those photons can bounce off you and come back to me for me to detect you. I love this stuff, guys. Let's do another one, all right? Let's talk about, not yet. Let's talk about the twin paradox, right? So here's the setup. We're going to have identical twins. One's on Earth and one's on a spaceship. And they're going to synchronize their clocks, right? They're the same age. And then one's going to go on a great galactic tour, fly around the galaxy, and come back home. And the question is, who aged more? Relativistic effects are in, they're moving fast enough. There's going to be time dilation. Should the Earth-based person grow older and see their younger twin? Or is it the other way? We just said that the fast-moving object is going to have time dilation. So we tend to think in this picture. We'd say, hey, I'm on Earth, they went on a rocket ship, they flew around the cosmos, they were fast-moving, and therefore their clock will run slower, time dilation. But doesn't the person on the rocket ship have equal validity to say, look, I lived on a rocket ship and I saw my sister on Earth fly away at great, tremendous speeds? And this is the crux of the paradox. Who has the correct claim of who flew away? So there are tons and tons of articles on this. Great detail on this. I'll tell you just short. The answer is going to be that the Earth-based twin will be the older one. The reason being is that you have to account for the accelerations, right? One person is on a ship that flies away, and all of our concepts in special relativity, they work in inertial frames. Well, if you're a rocket ship flying away, that rocket ship has to eventually stop, turn around, and come back to us. And that process, that acceleration change to slow down, turn around, come back, or even if they loop around, that's still an acceleration change. That act, that process there, changes the physics significantly. And it does provide, you could think of it as a bias of saying there is a correct, and I do mean quotes here, but there is a correct frame of reference to measure things from. And because of that, the twin paradox is, yet again, not a true paradox. You just have to be careful and study the fundamental physics happening there very carefully. Now, speaking of twins, I feel like this is worth mentioning here. Not particularly relevant to relativity and black holes, but this comes up in the headlines a lot, and they get referenced now a lot when you do like a simple search of these. And yes, there are twin astronauts, right? Mark and Scott Kelly, right? Scott spent about a year in space, and it's worth commenting on that there's a lot of misleading headlines about what happened to Scott's biology. The most extreme example I saw was that his DNA, Scott's DNA, changed by 7% from being in space for a year. All right, so I want to dispel this now. Right? Yes, there was a time difference. Scott being in space did experience a different amount of time transpire. We're talking on the scale of nanoseconds over the course of that year, maybe microseconds difference, right? A blink of an eye is longer than that. But, all right, fair. They did technically experience different amounts of time transpire in their lives. Right? The other thing that did happen was that this was a great experiment biologically. Scott had samples, biological samples taken from blood, probably be an example, maybe some tissue samples. And that was done before and after his trip in space. And then that was also compared to his twin brother. And that's where the idea of which genes were active. They're trying to study the biological impact of living in space. Right? And so that's the origin of all this information about the twin astronauts.